Okay. Ooh, the camera's a little closer. Once this works out okay. Okay, so chapter 3. I'm going to go over chapter 3 real quick in the textbook. The key ideas. Oh, man. Okay, so the first thing that they have in there is position versus displacement. So here, let's say here's my xy axis, and here I have some object, and it goes and moves over there. So it goes from there to there. Okay. There are two things that are important. The first is position. Position is where is that object at. So this depends on where your coordinate system is. So here I'm going to call this vector R1, and we're going to call that the position of this object. It tells me where it is. Okay. It doesn't really matter. It does matter where the origin is. Okay. So if I have a different coordinate system, I'm going to have a different position, but the object's still in the same wherever it is. Okay. And then I can find another position over here, R2. So we use the vector R. We use the symbol R because, we're dealing with 3 dimensions here. We don't want to say X, Y, or Z or anything like that. So this is a vector. It includes all those coordinates in there. So I have 2 different positions. Now, what I really want is the displacement. So that's the vector from the starting point to the ending point right there. And I call that delta R. So delta R is the displacement. And you can see here that I have a triangle. It's not R1 plus delta R is equal to R2, right? Just because I start here, I put the next vector at the end of that one right there, so I could write this as R1 plus delta R equals R2. But really I want R2, so I could solve for this. I can algebraically solve for this and get delta R equals R2 minus R1. And remember I said this is one way to do vector subtraction. This vector minus that vector is from the beginning of R1 to the end of R2. Okay, so this is going to be important. It doesn't look very important right now, but it is. And so whenever we see the triangle like that, delta, that means change in. So this is change in position, and that's exactly what that is. Okay, so this is R is position, delta R is displacement. They're both vectors. Okay, why do you even care? Well, we care because that's used in the average velocity. So if I want to define average velocity as a vector, this is a V. It's going to be delta R over delta T. So it's a change in position over the change in time. Okay. So if I have that as a vector, I can. How do you divide a vector by a scalar? It's not so hard. Okay. Let me write it as the book writes it. Let's say I have. Let's say I have delta R. Delta R is equal to, I'm just making up something here, 4 meters x hat plus 8 meters y hat. And then if I have my delta t is 2 seconds, then average velocity would be delta R, so it would be 4 meters x hat plus 8 meters y hat, all of that over 2 seconds. So when we divide, you could probably guess that I would have to divide both of those by 2, and you would be right. Okay, so this would be 2 meters per second x hat plus 4 meters per second y hat. So I still get a vector. Okay, you can't divide a vector by a vector, but I can divide a vector by a scalar, and that's what I did right there. Okay. What about one of the things that you'll see a lot is a graph. If I plot the time and just the x position on some object and say it looks like this, well, how can I find the x velocity? So here, that's the average velocity. The average x velocity would just be delta x over delta t, just the x component. So if I do that, if I take 2 points right here, and I do the change in x would be this, and the change in t would be this. And so if I take delta x over delta t, that looks exactly like the slope, and that's what it is. The slope of this line of x versus t is the average velocity. V average x is the slope. Now, what if I look at down here, if I look at the average velocity from here to there, that's my slope. Okay? And that doesn't look like it really matches the graph very well, because what's happening here is the velocity is actually changing as you move along. Okay? So, in this case, the average velocity and the instantaneous velocity are different. The instantaneous velocity is the tangent to that curve. So v instantaneous in the x is going to be the limit as delta t goes to 0 of delta x over delta t. So as I let those 2 points get closer and closer together, I get a better answer. Okay, 3 more things. I'm trying to go quick because I don't want to make a 20-minute long video. Okay, the next thing, I wrote it down here, the nature of force. I don't think this is the best way to do it, but this way the book does it. F net equals ma. This is what you'll see. Oh, sometimes you'll see 1 over m F net equals a. That's another way to put it. But this says something very important that people have trouble with. This says that the net force is proportional to the acceleration. Okay? And we define the average acceleration as delta v over delta t. And this is important. This says forces change the velocity. Force is not velocity. Okay, so this is the average acceleration. We're going to deal with cases where the acceleration is almost always constant, such that the average acceleration is the same as the instantaneous acceleration. Okay, one last thing. Let's say that I'm on a bus. I'm standing on the top because, you know, that's what I like to do. And I can throw a ball, I can throw a ball at, say, 10 meters per second. If the bus is going 10 meters per second also, and I have someone on the ground, how fast would they see that ball moving? I can throw it 10 meters per second, but the bus is also moving 10 meters per second. Okay, so here we have a problem of I can throw this ball relative to the ground at 10 meters per second. But what would someone see me if I'm on the bus throwing that ball? And this is what we have with relative velocity. Velocity that we measure is relative to our frame of reference. So if our frame is moving, we're going to have a different value for the velocity. And it's a vector too. So let me just say this particular case like this. I can call this the velocity of the ball with respect to the ground. I'm sorry, W is not ground. Okay, that's this. And then I have the velocity of the, maybe that's a car, it's not a bus, it's a car. The velocity of the car with respect to the ground is that. And I want to find the velocity of the, I'm sorry, this is the, I keep messing up. If I'm on the bus, I'm going to throw the ball, it's going to be the velocity of the ball with respect to the car, and have the velocity of the car with respect to the ground. Then the following is true, the velocity of the ball with respect to the ground, it's going to be the velocity of the ball with respect to the car, plus the velocity of the car with respect to the ground. So these are vectors, so we have to add them as vectors. But here you can see this, the trick here is this notation. If you do object with respect to frame, and then frame with respect to another frame, then with those things match up right there, then I get ball with respect to the ground. Okay. Now I'm going to give you an example of this somewhere else, but this is, you'll see stuff like this when you have a plane flying with respect to the wind, and the wind's moving. Then you can say the velocity of the plane with respect to the ground is equal to the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground. And those are vectors, so it matters. And drop on this stuff. Okay, so that's what's in Chapter 3.